Let's go. Start now. Me to move. So, good morning, everybody. Let us not waste our energy and do everything we have to do on time. There are a lot of things to do, and in a single day, just a single day can make a lot of difference in your life. Just a single day. So, as much as possible, I would like you to take this so serious. So, I want you to take it so serious. If we take all of the topics one after the other, it might take us a bit of time, but I'll try as much as possible to use 1 hour per topic. And I want to believe we are all here with our past questions. So by the time I want to start solving question, if I can't see your past question, then you are going out. So because those were the instructions and rules I've been reposting. So even if you don't have, you should have followed, so that we do all it all together without wasting time. So there are a lot of topics. We will do physical chemistry today. So we'll cover all the physical chemistry, we'll cover inorganic chemistry, and we'll cover organic chemistry. So I will start with physical chemistry. When I'm through, I'll give you like 30 minutes break. Then after that, I'll start inorganic. I'll give you like 30 minutes break. Then we'll start organic. Then we will solve all the questions. And I want to believe you have tried watching YouTube videos on every of the topics, like I gave you instructions. The reason for that is to make us be very fast so that you understand it. Now, I'm just going to walk in line with Jan. You might have watched YouTube videos and they might have taught you different things that might not even be necessary, but at least you have idea. So the way to go in line with JAM or WAEC or any other exam is what I'm going to quickly explain today. And I want us to pay attention all through the class. Where's the blue mark? Okay. So from the topics you gave me, I think we're going to touch, you have seen the topics I listed, but nobody wrote oxidation and reduction, and nobody wrote electrochemistry. I know you had a full Saturday to do that, but for the sake of those that just joined, I'm still going to just touch it. I'm going to touch it again, but I won't start with that because you didn't write it. So I will start with all the ones you wrote. Thermochemistry, chemical kinetics, chemical equilibrium, acid, base, and salts. All those ones are what I'll touch first. So if you now have any other one, so let's say TT1, we should be able to be through with those ones. Then maybe between 2 and 3 to 4, we should be through with inorganic. Then latest by 6, 7, we should be through with organic. So let me start with thermochemistry. And I'm only going to be breaking it down in order not to waste time. There is no notes, but just understand. Then one thing I will do again is that when we are through, we are now all going to carry Ababio. I don't know if you have Ababio. I will show you some parts of Ababio. You should go and, even if it's a day to your exam, just make sure you go through those parts. Before you go for your exam at all, just make sure you go through those parts from beginning to the end. And I'm sure of 90 something for you. So let's talk about thermochemistry first. You call thermochemistry heat changes. So I'll be time conscious as well. This is 15 minutes past 8. So those that are online can share with every other persons. So for thermochemistry, you would have had in your textbook, in your normal textbook, it is called heat changes. So this part here, thermo from thermometer, usually means heat. Then chemistry talks about chemical reactions. Please send me to inform Elizabeth that wants a blue or black marker. This marker is green and is fading. So for thermochemistry, we are trying to study heat changes. So please, let's pay attention. And if you come late, don't come to the front. Don't disturb us, please. For thermochemistry, we want to study, everybody should pay close attention. I will ask you questions when I'm through. For every 2 plus O2 to give 2H2O. In this reaction, before hydrogen will react with oxygen to give water, I have to break the bond between hydrogen. I have to break the bonds between oxygen. Then I have to form new bonds between oxygen and hydrogen. Now, I broke this bond. I'm breaking this bond. I will use energy. I'm going to use energy. Here, I'm going to form bond. Whenever I'm forming bond, I'm going to release energy alongside. So now, in this case, every time you're talking about chemical reactions, energy is usually involved. Energy is involved. Either the energy you use in breaking bond or the energy you use in forming bond. Energy is involved. But now in chemistry, there is no way for me to measure that energy. So the best thing I can do is to measure what we call heat. Heat is a form of energy. Do you agree? In physics. So if I want to measure energy in chemistry, the only thing I can do is to measure heat. So the heat that I measure can tell me more about energy. And that is why we are studying this topic. Do you get that? So when you study the heat changes that accompany chemical reaction, then we call it thermochemistry. That is the basic definition. Study of heat changes that accompany chemical reaction. Now, some reactions, I'm going to zero up the board and start properly. Some reactions can release heat, can evolve heat. If you carry out the reaction, heat will be given to the environment. What do you call such reaction? Exothermic. Why some reaction can take heat from the environment. If I bring ice block out and I put ice block on the ground, you know, normally the ice block will be taking it from the environment in order to melt. But if I put steam, hot water on a table, what will that hot water do? It will be giving it to the environment. Same thing we have in chemistry. When reactions happen, heat can either be evolved or taken from the environment. And that's why we start with the introduction. So you need to know something called a system. So if you understand the basic story I said here, you will know why we want to study what we want to study. Now, the first thing is what we call a system in thermochemistry. That thing you are studying, if I say ice water now, you know what will happen with ice water. Can you describe a lot of things about ice water? Yes. If I say acids and base, Abby. Now, if you are in the laboratory, you are carrying out a reaction. This reaction you are carrying out is what we call a system. Is that taken? That's the first thing you need to know. So I can have a system. This is a system. There is sodium hydroxide and there is what? HCl. You need to understand that. Now, this system, now, what type of reaction is taking place inside? Exactly. This neutralization now, what will it do? Can it give it to the environment? Can it take it from the environment? That's what we study in chemistry. So when you are carrying it out in the laboratory, it might either give it to the environment or what? Take it from the environment. Do you get my point? So now, that thing is reaction. CaCO3 to give CaO plus CO2. What type of reaction is this? Decomposition. But you remember something, that they always put something like this. What does that mean? Heat. That means that before you can break this guy, you have to what? Supply it. So this is a type of reaction that you have to supply it. This is a type of reaction that usually give heat. Is that taken? So what we are studying is the amount of heat gained or what? Heat loss to the what? Environment. So that's why we have another term called surrounding. Surrounding. So surrounding is, if you understand this, then every other thing will be very easy. So everything you have around the system is called what? Your surrounding. So everything around this guy now is called surrounding. The laboratory where you are carrying it out is called surrounding. Then the region between, because there are some terms they will be using, when you touch it, will it be hot or cold? That's why you have what we call boundary. Boundary. So the boundary is the junction between the system and the surrounding. If I put hot water in a stainless and I put hot water in a plastic, hot water in a plastic and hot water in a stainless, and both of them are in the same surrounding, they are in the same place. Now, when you touch the plastic and when you touch the stainless, you feel the difference, Abi? One feels hotter to your touch, one feels cold, not really colder, but not so hot, Abi? Now, that is what we call boundary. So the boundary for stainless is different from the boundary from plastic. I'm only using those terms to make it make sense. If you are carrying out reaction in a conical flask, you know how conical flask is, Abi, if you have done basic type neutralization before. So that junction between the system and the surrounding is called what? The boundary. That place you can touch is what we call the boundary. Now, we now have two types of systems. Quickly, we have three types of systems. Now, when you're talking about system, all these things are not so important now, but because they will not really ask you, but they use them to ask you questions, and that's why I'm explaining them first. So now we have three types of system. We have what we call an open system. Please help me to get a better marker, please. We are not the only one in this class. We have what we call an open system. We have what we call a closed system, and we have what we call an isolated system. So when I get to chemical equilibrium now, we'll be mentioning something like a closed system. So you should understand what I'm saying. So if I say open system, if I carry out reaction, an open system loses both energy and matter. So an open system, from the word open, is something that you left open. Let's say I have CaCO3 in this place and I'm heating it and it gives me CaO plus CO2. Now I'm supplying heat, so there is an exchange of heat, Abi, with the system. That's number one. Then number two is that we'll be producing a gas. Can you see that? Now that gas I'm producing, what is the tendency for it here? It can escape, Abi. I hope you're getting that. That's what an open system is. So a system is said to be open when it can lose what? Matter. Matter is just like gas, Shebi. So when it can lose that gas, or when it can lose energy, and what is that energy? Heat. So you are not protecting it. It can lose heat to the surrounding or take it from the surrounding. Then you call it an open system. Now, a closed system, from the word closed, is a system that cannot lose. Follow, so that when we are solving questions, you get it right. I'm not going to give you notes because you don't really have much time, but the way I'm explaining it, let your brain follow and be jotting what you can jot. And that's why I say you should try your best to at least watch it too. Now, a closed system, what is the difference between a closed and open? Closed loses both energy and heat. Why? And both energy and matter. Why closed does not lose matter? Because you have closed it. Abi. So if you carry out reaction in a system that you did not open, matter will not be lost, but energy can still be lost. So the difference between these three is just what we now call isolated system. Isolated system is the one that you protect. That's what you do with calorimeter. You protect it so that there will be no heat loss. You are not losing it, and you can see that it's also closed. You are not losing matter, so you don't lose heat. Neither do you lose matter. Is that taken? So you too, you should learn a shorthand of writing. It's not everything that you don't lose heat, you don't lose matter. Just put X, meaning heat and matter, meaning that you don't lose heat and you don't lose matter. Is that taken? At this stage, you will need to be someone that knows how to write and understand what you have written. So get used to it from now. Some lecturers will not wait for you to do anything when you get to university, and we want a short time. So now that we understand these basic things, there are a lot of things, but now that we understand these basic things, let's now go deeper. If I want to study heat in chemistry, we focus on this term, enthalpy, but I'm going to just use the word standard straight. Standard enthalpy. That is, we represent it as, let me put standard enthalpy change. Please, let your mind follow what I've said so far. You will have time to study everything. At least when we finish today, you will know that it's just for you to be solving questions to your exam. So now, we represent it as delta H naught. Delta H naught. That is called standard enthalpy change. If I want to tell you that it is given by a reaction, I will give you a value for this. When I give you a value, when you see it, you can tell me that, oh, it is given. So if I say delta H naught is negative, I mean that immediately you see that the conclusion is that, oh, please don't start sleeping. We have not even started. Please, I mentioned it in class that you should conserve your energy very well before you come, because you go throughout the day. And the more you start sleeping, I will ask you to step outside so that you go and sleep properly. So now you cannot be using your own energy to affect our energy. So if I say delta H naught is negative, it means that reaction. So if I can give you something like this, let's say A plus B to give me C plus D, and I say delta H naught is minus 320 kilojoule per mole. Now, immediately you see this. This is a reaction now. Everybody look up. Immediately you see this. What does this mean? That means that when A reacts with B to give C plus D, it is given out. Is that taken? Now, if it is a closed or open system, they will tell you. But for now, you can tell if it is giving it or taking it. And if I say that for this same reaction, delta H naught is positive, this is telling you that it is what? Taken from the environment. It's a common knowledge. Now, look at it. That word, this guy, this H is what we call enthalpy. This delta is what we call change. Then this naught is what we show standard conditions. So when I measure the heat change that follows a reaction under standard condition, then we call it standard enthalpy change. So the heat change that follows a reaction under standard condition, that is what we call what? Standard enthalpy change. Now, your standard enthalpy change can now either be it is giving it to the environment or it is taking it from the environment. So let's now see the terms we use. So when we have delta H, what do we now call this delta H? It is the one that measures the heat gain or loss. So in a simple term. So what does delta H tell you from the stories I've said? If a system is losing heat or what? Gaining heat. Is that taken? That is it. You are still going to have the video on YouTube later. So in case something is looking, you can go and watch it again calmly. So what does delta H measures? So if I say that delta H is negative, what does that mean? It's loss. Abi, when I say it is positive, so that is what delta H measures. So how do we measure this delta H? It depends on the reaction. But we can use a graph to measure it. So quickly, let me give you the graph. I can rub this part. Do we understand here now? So a system can either lose it or what? Or gain it. So let's rub this part. So now, in exam, what they will ask you is around this area too. They can ask you this one, that when the H is negative, what does it mean? And it's a general thing you did in SS1. But we are going to build on it. So now, graphically, when reactions happen, we need to know something. There are two types of graphs we used to have. I have a graph like this. This part here represents my reactants. This part represents my products. So let's say A plus B to give C plus D, right? That is what I have. So my reactant will be what? A plus B. Abi, my product will be C plus D. Now, I want to know the delta H for this reaction. Will it be negative or will it be positive? So the question is, how do I know this delta H? There's what we measure. I need to know what we call the heat of reactants and the heat of products. Is that taken? If I know the heat of products, I know the heat of reactants, I can determine delta H. So the difference between the heat of products and that of reactants, if it's on the same level, if the heat for this guy, if this one is 50 and this one is 50, what will be the change? 0, Abi. But if one is more than the other, so if reactant is 100, let me put it here, 0, 50, 100, 150. Now, if I ask you, what is the, these are the questions that we ask you. What is the heat of products here? 50. You just trace it. You know how to do graphs. So you just trace it. This is energy and reaction coordinates. So, what is the heat of reactants here? So now, if I want to determine delta H now, the formula is, it will be changing or the sum of the energy of heat of products minus the sum of energy of the heat of reactants. That's how you determine it. So that means that of products minus reactants. This graph that I've drawn here now, is it going to give me a positive answer or a negative answer? Negative, because the product is like 50, Abi, minus 100, and that gives me what? So that gives me minus 100 kilojoule per mole. Now, from what I have here, since my answer is negative, what does that mean about this reaction? It is giving it to the environment. So I'm not using exothermic, endothermic yet because I assume you know it, but still let's go on. So now you understand this. We are going to now say a lot of things using this graph, but I want to believe you understand what I'm saying. Let's draw another graph. So if I have a graph like this, now this is 0, 50, 100. Now, note something. One of the mistakes students used to make. If they ask you that what is the delta H for this guy, this is your reactants now. Let's say this is your A plus B. This is your C plus D. That's the product, Sabi. So now, when you trace this guy and you trace this guy, so the difference between this and this, that is what? Your delta H. It is the difference between the reactants and products. Is that taken? So now, that means delta H for this is going to be heat of products minus heat of reactants. At the end, what is my heat of reactant products? 100. So for my heat of reactant is what? So 100 minus 50 is what? Is that taken? So this type of graph now, what does it tell you? It is taken from the environment. Now, what are the terms we now use? Let's quickly summarize it from what we have said so far. So these are the questions they can ask you. You can hear the word exothermic, and you can hear the word endothermic. So if your system gives heat to the environment, you said it is what? Exothermic. So your delta H will be negative. Your delta H will be positive if it takes it from the environment. Now, from what you have seen here, that means what does this graph represent? Is it exothermic or endothermic? Exothermic. Exothermic. So a graph. Now, note something. The heat of reactants here in this place, is it more than the heat of product? Yes. When the heat of reactant, you know, is around 150, is higher. When it's more than that of product, then you say it is what? Exothermic. So that means when heat of reactant is greater than heat of product, then you will also have exothermic. But here, when heat of reactant is less than heat of product, give heat to the environment. So that is what happens there. Now, in the next case now, quickly understand this. These are reactants. This place is usually called this place is called activated complex. Activated complex. But you remember one thing I said when I started? I said, let's say hydrogen plus, listen to this, so it's important, plus oxygen. That will give me what? H2O. Abi? I said we are going to break bonds here. The energy we need to break this bond is called bond breaking energy. The energy we need to form this bond is called bond forming energy. Is that taken? Now, I want to say something. H2 and O2, they represent my reactants, Abi, which means I need to break bond. Now, if I'm going to break bond, just note from year to year, because the reactant will climb here, then they will come down to form the product. That means for product, it will be from year to year, Abi. For reactant, it will be from year to year, like this height. You know, reactant will only have this place to climb. The product will have this place to fall. Are you following that? So now, if you look at this graph, between the one that wants to fall and the ones that want to climb, which one looks much? The one that wants to fall. That means that, where are we forming bond? Products, Abi. That means that this side will be your bond forming energy. Are you following? The one that wants to climb, that means that will be your bond breaking energy. Did you get that? Now, I now want to ask you another question. Bond forming energy and bond breaking energy, which one is greater? Bond forming energy. Very good. So now, if your bond forming energy is greater than your bond breaking energy, what will be the reaction? Will it be exothermic or endothermic? Exothermic. Do you understand that concept? So that means that the next thing you need to know is that when your bond breaking energy is less than your bond forming energy, then it is going to be exothermic. That's a common question. Then opposite. When bond breaking energy is higher than bond forming energy, it is going to be what? Endothermic. Are you following? So now the next thing you need to know is that you can compare them so that we don't waste time. Now let's say I have sodium chloride and I want to break it to give me sodium ion plus chlorine ion. The energy you need to break this sodium solid, we call it lattice energy. Before sodium ion splits like this, it might have been put in water. Then, at the end of the day, you form these products. Let me repeat myself. When you have a solid, the energy you need to usually break that solid, for simplicity, is called lattice energy. But you know, if I put sodium chloride in water, that's why you always see something like aqueous. Aqueous, when it is in water. That means that after you have broken, when you put sodium chloride in water, it will dissolve. After you have broken the bond between sodium chloride, then you are not going to form a new bond between sodium and water, chlorine and water. Now, that bond you form between sodium and water, we call it hydration energy. So for the reactant side, we call it lattice energy. That's what I want you to get. For the product side, we call it hydration energy. So when hydration energy is the energy released when you are forming a bond between ions and water. Now, from what you have here, I'm using another term. Lattice energy can also be like what we call bond breaking energy. You know, it's the one on the reactant side now. So which means that, can you see what will happen? If I want this reaction to be exothermic, that means my lattice energy must be lesser than hydration energy, if you are following in spirit. Let me repeat that. I have sodium chloride dissolved in water. Then this gave me sodium aqueous. There's a way to form in water, but I'm just telling you. They always tell you that anytime you dissolve a substance in water, it will become an aqueous, Abi. Then, you know, this is a solid, Abi. What energy will you need to break it apart? It is called lattice energy. So that's a question they can also ask you. The energy to break solid apart is called lattice energy. Now, when you break it apart, it's going to form a bond with water. That bond with water, what do you call the energy? Hydration energy. Do you get that? Now, which one is your product out of lattice energy and hydration energy? Hydration energy. And we say when energy of reactants is higher than energy of products, it will be what? Exothermic. That means when lattice energy is higher than hydration energy, it's going to be what? Do you get the terms? So that means that this part now can be your lattice energy. Why this part can be your what? Hydration energy. Just for simplicity. So it is going to be exothermic when lattice energy is greater than what? I mean, it's less than hydration energy. Then opposites for endothermic. Are you picturing what I'm saying? That's chemistry. You must be able to picture everything in your mind. It's not so hard. Now, another thing is this. They cannot tell you that the reaction is exothermic. If, let's imagine that, thank you, the system, this is a system. I want to believe you understand what system is now. That is what I'm studying. If it is exothermic, when you touch it, how will it feel? Is it cold or hot? If it is, what is exothermic? Is giving heat to the environment, Sabi? So if something that is giving heat to the environment, when I touch it, what will I feel? It will feel hot, Sabi? It will feel warm. Do you get that? So that means the exothermic reaction, when you touch the vessel or container, it is usually warm, Abi? But the one taking it from the environment, if you put ice water in a stainless plate and you touch the plate, it feels cold. But the ice water to break apart to take heat from the environment. Is that clear? So now, that means this one feels cold to touch. All these are common questions you can see. So those are the common things you need to know about exothermic and endothermic. So it feels warm and it feels cold to touch. Now, the next thing to talk about are now the types. We have different reactions, but I'm just going to talk about 3 for this class. Please, do we get the light of that now? You can digest it, think about it again. So quickly, we have different reactions. I'm using the word reactions so that it will make sense to you. But for all the enthalpy change, everybody, delta H naught. What did I call this again? Standard enthalpy change. Standard enthalpy change. Now, let's say I have, let's just say A plus B to give me C plus D. 2 moles, 3 moles, whatever the products are. Then I will measure the standard enthalpy change. But you will see something that will put around here. What I put around here gives me information about what this guy is talking about. If you see this out now, that R means reaction. reaction. So when you see delta H naught R, that is called standard enthalpy change of reaction. When you see delta H naught C, that is called standard enthalpy change of combustion. Then when you see delta H naught F, that is called standard enthalpy change of formation. And when you see delta H naught N, that is called standard enthalpy change of neutralization. These are the four important ones for now, for your sake. Now, let's pick them one after the other. Let's say I want to pick a reaction that has nothing to do with. Let me even start from this one. So I'll come and round it up with this so that you understand it. Now, let's say I have carbon. I burn carbon in oxygen to give me CO2. Then I set delta H naught for this C is negative. I'm not going to say much about it. Now, what does this represent? Standard enthalpy change of combustion. And when you hear the word combustion, when a substance, this is the substance now. But you can see that this guy, negative means what? He's releasing it. When a substance burns completely in oxygen to give something, then we call it combustion reaction. So now, this is the substance I'm focusing on in this place. So the definition is that when 1 mole of a substance burn in oxygen to give whatever product it is, when 1 mole of a substance burn completely, what is the substance that is burning in oxygen here now? Carbon. That's your focus. 1 mole of a substance burns completely in oxygen to give its product. You don't need under standard condition. Then we call that standard enthalpy of combustion of carbon. Is that taken? Look at this. But under standard condition, don't forget that word 1 mole. Look at this. H2 plus O2 to give half H2O. I have to put that there because I want to make this in 1 mole. Now, if you look at, I'm coming. A2, I think that's okay. So now, if you look at what I have here, delta H naught C. Everybody, how will you interpret this? Quickly. Your mind has to always say all these things. It gives you knowledge when you are studying and when you are solving questions. I don't want to use more than 1 hour for this class. Then before we solve questions, I'll move to the next one. So yeah. Exactly. What's your focus? Standard enthalpy change of combustion of hydrogen. Do you understand that English? But yeah, now what would I call it? Standard enthalpy change of combustion of carbon. That's the statement. But this thing, I can still write it in another way. You should understand what combustion is now. When 1 mole of a substance is completely burnt in oxygen, we call it standard enthalpy change of combustion of that substance. Is that taken? Ademile. So if I have this, and I give you this, delta H naught F. Everybody, what did I say delta F means? Formation. But now, how will you interpret this one now? Standard enthalpy change of formation of water. That is it. Not hydrogen again. What did you form here? Water. That's where the word comes from. Formation of. But when you are saying standard condition, it must be 1 mole. So if you misplace that word 1 mole, your answer might be wrong. So this is called standard enthalpy change of formation of water. You are no longer saying burning of hydrogen. Burning of hydrogen is different from forming of water. Do you understand that statement? Drop it. Who is there? Drop it. Maybe there are people online that cannot see. Are you sure you are following? Oh, Mama, you might drop it. Oh, my show. We started class this morning. People did not allow us to pray. Let's close our eyes and pray. Dear Father, we thank you for another beautiful morning like this. We thank you for a moment of learning under your feet. Lord, we say be thou exalted in the name of Jesus. We thank you for our mind of understanding our hope on this morning. We have wisdom from above to comprehend, understand, and apply everything we are going to learn today in the name of Jesus. I that you are using, I have no brain of my own, but I want you to engineer my brain, work in me, and use me for these people today in the name of Jesus. I have wisdom directly from above in the name of Jesus. At the end of our exam, it shall all be testimonies, not east, west, and south in the name of Jesus. Thank you, Heavenly Father, for answering our prayer. The strength to carry on today, Lord, you give unto us in the name of Jesus. All the people that are sleeping, Lord, you excite them in the name of Jesus. In Jesus' wonderful name we have prayed. Amen. So, hallelujah. Now, from what we have here, delta H naught F is called standard enthalpy of formation of water, standard enthalpy of combustion of hydrogen. Those are the things you need to understand. So, if I now give you a value like this, I'm just going to be giving you some random values, but because your understanding is what JAMB will test, is not the stories. So let's say I give you something like this. Let's say I have H2 plus half O2 to give me H2O. And delta H naught F is equal to minus 57.3 kilojoule per mole. So everybody look up. From what we have here now, this, how can you interpret this equation in thermonuclear term? The standard enthalpy of formation, the standard enthalpy change of formation of water is what? Minus 57.3 kilojoule per mole. Which means that what? This reaction is what? Giving it to the environment. I now ask you a question, I now give you this. And ask everybody, what will be the standard enthalpy of combustion of 1 mole of hydrogen? A, 57.3. B, minus 57.3. C, 57.3 times 2. That should be like 114 there. Let's just say 114.6. D, minus 114.6. So, if the standard enthalpy of formation of water is minus 57.3 kilojoule per mole, calculate the standard enthalpy of combustion of hydrogen. What would be the answer? Minus 57.3. It's the same thing because we are just using different terms. Do you get that? I could have written this as delta H naught C. But by the time you see it as delta H naught C, what will you call it? Standard enthalpy of combustion of 1 mole of hydrogen is minus 57.3 kilojoule. Note something. If I flip this over, if I say, because they might ask you, if I flip this over and I have H2 plus, and understand this, we will apply it soon. Delta H will now become plus 57.3. So the difference between the first and the second is that you flipped it. When you flip reaction, the sign will also change. That's what I want you to know for now. So when we get to chemical equilibrium, I'll remind you this, that forward reaction, if it is exothermic, reverse reaction will be what? Endothermic. And that's what I just showed you there. Another thing is this. If I have So, from what I have here, I said this is A, this is B. If the standard enthalpy of formation of water is minus 57.3 according to this reaction, calculate the standard enthalpy of formation here for water. What would the answer be? Did you get that? Why? Because it has changed from 1 mole now, it has become 2 mole. So you have to multiply this by 2. Those are the conditions. First is when you flip it, the sign changes. Abi, when the values also change, you multiply it by that value. If I put half here now, that means you must divide this by 2. Do you get that concept? Those are the likely things you see in the exam. So now let's move on from formation. So we understand the difference between formation and combustion now. Now, neutralization. Neutralization is just, this is what we call neutralization. You remember, you said that when, sorry, this is supposed to be like a base, Abi. So now, when hydrogen reacts with hydroxyl, or when a base reacts with an acid, you form salt and water, Abi. But in reality, in neutralization, what you form is what? Water. This is the acid, Abi. This is the base. Then you have water. So if I now represent it as this, then what are we going to call that? Standard enthalpy change of neutralization. So if they now say you should define it, this is the amount of heat evolved when 1 mole of hydrogen ion reacts with 1 mole of hydroxyl ion to give 1 mole of water under standard condition. Then we call it standard enthalpy change of neutralization. It's written on the board. What I've said now is written on the board. Standard enthalpy change of neutralization is defined as the amount of heat evolved. Heat is always evolved. I will give you that. When 1 mole of hydrogen ion reacts with 1 mole of hydroxyl ion to give 1 mole of water under standard conditions. Then that is what we call standard enthalpy change of neutralization. Now, let's move on from there. We understand these three now. Now, reaction. When it involves everything, then we call it reaction. Let me rewrite that equation. So I will ask you questions one by one when we start solving questions. Sodium hydroxide plus A2SO4 to give Na2SO4 plus 2H2O. Then I now write delta H naught R. Now, let's look at the difference. When I talked about combustion, I said it is the amount of heat involved when 1 mole of a substance is burnt in oxygen. Abi? When I talked about formation, I said it is the amount of heat involved when 1 mole of a substance is formed. When I talked about neutralization, it is the amount of heat involved when 1 mole of hydrogen ion reacts with hydroxyl ion to give water. Now, for reaction, it's focused on everything. It is the amount, for this reaction now, it is the amount of heat evolved or absorbed when 2 moles of sodium hydroxide react with 1 mole of H2SO4 to give 1 mole of Na2SO4 and 2 moles of water under standard condition. Do you see the difference now? So reaction focus on what? Everything. Is that clear? Now, if you look at that of reactions, there's a way we now do calculation. How will I know what is involved or released here? Then we say that the standard enthalpy of reaction is given as sum of the enthalpy of number of moles involved, products minus sum of the enthalpy of reactants. Let me just say So this is the formula to calculate standard enthalpy change of reaction. Is that clear? Now, quickly, with this formula now, if I know this enthalpy of formation of this guy, enthalpy of formation of this guy, enthalpy of formation of this guy, and that of this guy, I can calculate for everything. So which means that if I want to solve for this guy now, I would say that the standard enthalpy change of reaction is equal to products. What are my products? Na2SO4. That means I need to know the standard enthalpy change of formation of Na2SO4. Then I will add it to that of water. But water is 2 now, so I'll put that 2 outside. And I'll say standard enthalpy change of formation of water. Then that is for products now. Then minus that of reactants. So then for reactant, I'm going to have 2 into NaOH, standard enthalpy change of formation of NaOH, plus, which one is next? It's standard enthalpy change of formation of H2SO4. So that's the formula. So that's the general formula, all measured under standard condition. So the moment you know that of Na2SO4, H2O, H2SO4, NaOH, you can calculate for the reaction. And this is also a question they can ask you. For this case, you have to be careful of signs. That's why you see me putting compound bracket, and all of those things. Now, did we get it to this level? Now, let me tell you some things to note quickly. Then I'll move from there to, I'll just define Hess law. We have not spent 1 hour. So I'll define Hess law. I'll define, what's it called? The entropy, enthalpy, the laws of thermodynamics, and I will end it quickly without wasting time. Then we'll solve some bit of questions, then we'll move on to chemical kinetics or chemical equilibrium. Can I rub the board now? So let me now show you some things to note about these guys. Every time you talk about combustion, heat is always involved. Every time you talk about neutralization, heat is always involved. Is that taken? Anytime you want to measure enthalpy, we use what we call calorimeter. That's the instrument. To measure enthalpy, then we call it, with the instrument we use is what? Calorimeter. For enthalpy of combustion and neutralization, know this formula that delta H of either combustion or neutralization is given as Q over N. Now, Q represents what you did in physics, NC theta over N. So they will give you the mass of whatever is burning in oxygen, then the, what's it called, specific heat capacity of that substance or water, then the change in temperature. I don't have time for the experiments, we would have done it, but when we start solving questions, we might see it, so I will explain it to you. Is that taken? So now note this formula for either combustion or neutralization. Then the next thing you need to note is this. So don't forget, when you solve this question and your final answer is positive, you must pick what? A negative answer. Because combustion and neutralization is always what? Negative. So even if you solve and your answer is positive, you must pick a negative answer. That is that. Then for formation, there is nothing like standard enthalpy of formation of an element. If an element is on its own without combining with another element, then the enthalpy of formation is said to be 0. So don't forget that. The standard enthalpy of formation of an element is what? 0. Let me give you a reaction to tell you what that means. Let's say I have this Thermit process, aluminium plus Fe2O3 to give Al2O3 plus Fe. When I'm done teaching you everything I want to teach you, all the things I'm teaching now, there are things you need to know normally yourself. That anytime they ask you in chemistry, you answer them. These are common things. Then we'll still look at all the things that most people don't know that makes you score 98. We'll look at that together. That's what we'll round it up with. Then, as from today to your exam, just go and be solving questions on chemistry. Just pay attention, please. So from what we have here, I want to give delta H of this guy. You already know what this means, Abi. So that is the standard enthalpy of reaction, Abi. That means when 1 mole of blah, 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 is not balanced, Abi. This will be 2. Oxygen is 3, right? Iron will also be what? I think that's balanced. So now, if they ask me to calculate the standard enthalpy of reaction here, I will use my formula. Delta H R naught is equal to that of products, Abi. But now, that of products, we have standard enthalpy of formation. Standard enthalpy of formation of what now? Al2O3 plus, I'm supposed to add it to that of iron, Abi. But that of iron will be given 0. So anytime you have an element on its own, the standard enthalpy is taken as 0. Are you getting the formula now? So now, minus that of reactants, then that will be what? The standard enthalpy of formation of what? Fe2O3 plus the standard enthalpy of formation of aluminium, but that would be 0. Do you get that? So when you are doing your calculations, if you see elements on its own, it will be given what? 0. Is that taken? So that's what you do for formation. That's what you need to note. So for now, do you get everything we have talked about? So for formation, it can either be positive or negative. For reaction, it can also either be positive or negative. But combustion and neutralization is usually negative. There are some things that when they tell you, when you dissolve ammonium chloride in water, those are examples. I'll show you those ones later from the textbook. Those are general knowledge that you must know, aside all the things I've taught you. So the JAM can just ask you those ones directly. So if you have not read deeply into those parts, you might forget or not even know it. So, but let's just go on. So now let's quickly talk about what is Hess law. I'll just give you the definition of Hess law. The most times do not ask you questions in JAM on Hess law to be doing some. Oh, sorry. You should be able to write it now. You know what I've written there. Standard enthalpy of formation of Fe2O3 plus Sabi plus 2, 0. And you know why that is 0. So yeah, let's move on. So, let's do the paper. Please. You are going to ask your questions later. Why will remix be on your smartphone? Problems in it. Even me, I brought one past question. Oh yeah. So Hess law, for simplicity, it is called the Hess law of summation of enthalpy. Summation. So Hess law is just telling us that irrespective of the parts taken by a reaction, the total heat change is always the same. Either it takes a single step or several steps. If it goes from A to E, or go from A to B first, before going from B to C, before going from C to D, then now going to E. So Hess law is letting us know that what I want to get is A to E, but sometimes some reactions don't go straight. They first go through some other processes. It's not telling me that the heat I have here, for it to go from A to E, is the same as we have for it to go from A to B, B to C, and C to, just understand. So you can see the arrows. Extra is telling me that the total heat I will get if it goes from A to E will be the same as I will get if you sum how it goes from B to C to D to E. So irrespective of the path taken, the total energy you get is always what? The same. If I want to go from A to E, the total heat change will be the same as what I will have when I go from A to B, B to C, C to D, and D to E. Do you get that? So what it's just telling us is that you want to go from Songo to Elele, you can take different routes. If you go from Songo to Elele, and you go from Songo to Mokola to Dugbe, then back to Elele, Eslo is telling us that the total work you have done is the same. Is that taken for simplicity? That's what it just means. So in chemistry, I want to go from A to E, but I decided to go first from A to B, then B to C, then C to D, then back to E. Then it's telling me that the total work I've done, or the total heat change, when I go from A to E, is the same as what I've done in going all around. So that is what we call summation of the heat. So let's talk about entropy quickly. All these things, just have understanding of, there's a day we apply them. When you get to post-UTME class, we will be applying this law in solving questions. So you will see how we solve it. But in JAM, if they ask you, that will be those of you that have read deeper, you can solve it. It's very simple. You just sum the heat. Anywhere you need to flip, anywhere you need to cancel out, you cancel out. But it's a long thing that might waste our time. And even if they ask anybody in JAM, it will be like maybe one or two, maybe just in one batch. They can't ask several batches such question. So, but let's move on because we don't have time. All the likely things they have to ask you are the things I'm saying. So, if you are getting tired, you should let me know so I can give you exercise. Then we'll continue. Are you ready? We have not, we have several topics to do, and we are stopping physical around 1 before we start in organic chemistry. And we'll touch everything in organic chemistry too. So now, from what we have here, there's what we call entropy, without wasting time. Now, if you notice something, enthalpy that I've been talking about, this is a common thing you need to note. The unit is kilojoule per mole. Is that taken? That's the unit. Entropy. Entropy is called the state of disorderliness. State of disorderliness is what we call entropy. The reaction can be taking it from the environment and still be in disorder. Can be giving it to the environment and still be in disorder depending on conditions. So now, entropy is represented as delta S now. So if I have this now, this will be called standard entropy change. Standard entropy change. Entropy is also given as entropy of products minus some of the entropy of reactants. Now, if entropy is positive, it means entropy has increased. If you see that the answer is positive, just like what we have been doing, delta H can be negative, delta H can also be positive. If delta S is positive, it means that what? Entropy, disorderliness has what? Increased. If delta S is negative, it means disorderliness has what? Decreased. And if delta S is 0, it means nothing has changed. Now, what does that mean? Everybody, I'm going from ice to water. Entropy is called state or degree of disorderliness. Between ice and water, which one has higher disorder? Water. They are the ones that are free to move about. So if you look at what I have here, as I'm going from ice to water, Do I expect entropy to be increasing or decreasing? Increasing. So that means my delta S here will be what? Positive. Do you get that? So going from solid to liquid, let me just leave that. That has explained the whole story. Now, let me give you this reaction. If I have NaOH aqueous plus H2SO4 aqueous to give me that one I gave you the other time, Na2SO4 plus H2O. Just for question's sake, can you predict what the entropy should be? N2 plus H2 to give NH3. Can you predict what the entropy of this one too should be? Are you following? So we said degree of disorderliness. If it's increasing, then positive. If it's decreasing, negative. So, quickly. For the first one, what should it be? Because you're having liquid, being compared to aqueous. Is that taken? Yeah, now what should it be? Because you are going from, this is a gas, this is a gas, and this is a gas. So you are going from 4 mole of the gas, to 2 mole. So that means the gas is what? Decreasing. And if gas is decreasing, that means the disorderliness is also decreasing. So you expect this one to be negative. Why this one should? Is that taken? One more question. Everybody, what should be the delta S for this reaction? Is that okay? But you remember, this reaction, technically, do you expect it to be exothermic or endothermic? It's one of the things they ask you in JAM. You are going to supply it to this, to break it apart. So technically, you expect it to be endothermic, but it's still having what? An increase in entropy. So now look at what I have there. Let me stop there. Now you need to note this formula that delta S is equal to delta H over T. Please, they can ask you this in exam. So they will give you enthalpy change. And you might be the one to determine this enthalpy change yourself from all the stories you have been saying. After determining it, then you now divide it by the temperature, and that gives you delta S. But note the difference here. I told you that the units of delta H is what? Kilojoule per mole. All these are simple questions they can ask you. The unit of delta S is joule per mole per Kelvin. So whenever you want to use this formula to solve questions, be careful. If they give you delta H in kilojoule per mole, and you know that your delta S must be in what? Joule per mole per Kelvin. Temperature is already in Kelvin, but now, your joule, this one is kilojoule per mole. If this one is given in kilojoule per mole, that means you have to convert it to what? Joule before you solve. You just multiply it by 1000. Do you get my point? The unit for delta S is what? Joule per mole per Kelvin. Joule per mole per Kelvin. Is that taken for 1 mole of that thing? Then delta H is what? Kilojoule per mole. But anytime you want to use delta S equation, the unit is always in joule per mole per Kelvin. Joule, not kilojoule. But this one is usually in kilojoule. But if I want to solve a question on delta S and they give me delta H, that delta H might be given in kilojoule. Then I have to convert it to joule. These are simple things you are not careful of in exam. And you just put these values and you solve and you get an answer which is wrong. And you'll be surprised that why is it that you are not following 90 something. That is one of the reasons. Yaruka. Don't see. Raise your head up. So are we done? Do we get that now? Those are the things you need to know about entropy. So let's talk about enthalpy quickly. Second law also focuses on entropy, but let me just quickly give you enthalpy. Can I rub this part? Eh? I don't believe. I told you people to prepare your energy. I said you sleep. Yesterday now you are supposed to sleep all night. Throughout the day you are supposed to be watching YouTube videos on everything. Then throughout the night you are supposed to sleep. Because this is more like you want to touch everything you have done normally. So this is more important, even if you have not been attending classes before. So now, from what we have here, delta G naught is the next thing. So this is called Gibbs free energy. We will do physics, but we'll decide on when we'll do physics. So Gibbs free energy, we don't want to waste time talking. Now, at the end of the class today, we'll decide on physics. So for Gibbs free energy, this is called the available energy. Available energy to do work. This is one of the interesting topics in university. There are a lot of deep things we are going to be doing. Called. It's not online. Question. Please send me to pass. On time. I can. Which one did you say the entropy is 0? Is it this one? Someone is saying that the entropy of the second one is 0. God is getting. Manage. Yakubu. It will make sense. Just follow. Don't worry, we'll start solving questions. Just continue to follow. Now, this one, the delta S for this, is this supposed to be 0? No. The number of mole of the gases are different. Is that taken? So it's not 0. There's 4 mole here and there's 2 moles here. So it reduces. Then here, I go from solid to gases here. So it will increase. So please understand that. Some of you are saying that there are something that are new to me. How can we rewatch it? Don't worry, at the end I will solve questions on everything, those of you online. Then the video will still be on the live channel, so you can go and watch it later. So just continue to listen first. By the time you apply it, you will understand it. So delta G is called Gibbs. So please, let's come back to class. Delta G is called Gibbs free energy. That is the available energy to do work. Now, delta G formula is delta H minus T delta S. Everybody, what's the unit I said delta S will be? What's the unit of delta H? So the unit of delta G is also kilojoule per mole. So please don't forget this. If you want to use this formula, they most times give you delta S is joule per mole per Kelvin. So you have to convert it to kilojoule before you solve. Just note this formula. So what is the importance of delta G here? You use it to know the spontaneity of a reaction. Spontaneity of a reaction. You use it to know if a reaction is spontaneous or non-spontaneous. If delta G is negative, the reaction is said to be spontaneous. If delta G is positive, it is said to be non-spontaneous. If delta G is 0, then it is said to be in equilibrium. So please, this class, will be more important than whatever stories you might have been doing. Will be more important. Just make sure that you take your time. And if you are listening for the first time, it might still be sounding weird. And that's why it's even on the YouTube, so you can still watch it again. As you are watching, you are solving questions, solve questions. You will see that you will do well in your exam. So don't be discouraged yet. But as much as possible, the explanation is not that hard. So now, from what we have here, I don't want to say too much. You are going to get negative depending on this guy. So there's a question they can ask you, but in JAM, they don't like disturbing your brain. But because of time, if you look at this formula, at what point in time do you think everybody have to reason this along with me? Because that's the only area you might have issue in JAM to some extent from everything I've been saying. We said the reaction will be spontaneous if delta G is negative. Now look at this formula. At what point in time, that's the question you ask yourself, do you think delta G will always be negative? Delta G will be negative. Let me help your brain now. If delta H is negative and delta S is positive, every time delta H is negative, that means delta H is less than 0 or delta S is greater than 0. When this happens, delta G will always be negative. This aspect might sound confusing. Give them values and solve it. Give delta H minus 50. Give delta S plus 50. And give T maybe 20. Then solve it. You will see that your final answer will be negative. That's what I'm telling you. So every time they tell you that your reaction is exothermic and it has positive entropy, that reaction will always be what? Spontaneous. Are we okay with that? Let me repeat it. This is the formula your brain is thinking about. Now, this that delta G is negative. Anytime delta G is negative, the reaction is always what? Spontaneous. Now, you want this to always be negative. What will make it negative? When delta G is less than 0 and delta S is greater than 0. Sure. Don't go. At the end of the day, your delta G is going to be what? Negative. That's the condition. Those are the areas that only the intelligent people now might be the one that will cope. Or the people that have practiced for a very long time. But don't complicate your mind. To bá think of the most about the year, to bá ṣe àti wọlé lálẹ́ ṣá máa gbàdúrà kí question ẹ máa kọjá bí máa gbàdúrà. But èyí tí mo sọ yìí ó require some level of practice. Let me put it that way. Some level of IIQ. So delta H being negative, delta S being positive, then it will be what? Always spontaneous. I don't want to waste time. There's a lot to do today. I'm not supposed to talk about it, but I'm talking about it. Now, the second condition is that if delta H is positive and delta S is also positive, your reaction can either be spontaneous or not spontaneous, depending on the what? Temperature. But this is how you will know. Now, let me give you a graph that can give you the easy way. If you look at this graph, and you look at this graph, between graph A and graph B, which one do you think will stress the reactant more? For when we get to chemical kinetics, you will see it. For reactant to form products, then we have to climb. For them to form products, then we have to. So this one is likely to occur than this one. So anytime it is exothermic, it is likely to occur. But anytime it is endothermic, it might be struggling. So what you can do is you can supply it. Endothermic means it's taking it from the environment, Abby. So if you want it to occur, then you have to supply more heat. So which means that if delta H is positive and delta S is positive, that favors it. But if delta H is positive, you must supply it. You must increase temperature. This is what you should now focus on. So if a question tells you that delta H is greater than 0, delta S is also greater than 0, at what condition will this reaction be spontaneous? Then since delta H is greater than 0, that means it is positive. That means it is endothermic. And when it is endothermic, it wants you to supply it. So you must increase temperature to make it spontaneous. Let's leave it. So these are things that is not far-fetched, but don't worry. So for substance to go from ice, let me put it that way, to gas or water, and to go from liquid to ice, 1, 2. Which one is likely to happen on its own? That is what we mean by spontaneity. A reaction is said to be spontaneous if it occurs on its own without assistance. If I want it to go from liquid to ice, I have to put it in freezer. I have to change the condition. But if I bring that ice out, automatically it will melt. But it can never go back to ice on its own. So entropy is a constant thing. That's second law. So from what we have here, when delta S is positive, it is most likely to be spontaneous, occur on its own. When delta S is negative, it is most likely not to be spontaneous. Do you get this? When delta H is negative, most likely. When delta H is not most likely. So if they now tell you that delta H is positive and delta S is positive, look at this now. Is this likely to be spontaneous? Is this likely to be spontaneous? That means that one is disturbing it, one is supporting it. That means your delta G now can either be negative or positive. But if you want it to be negative, the only thing you can do is that you will supply it because it is endothermic. So you will continue to supply it. That will make it negative. So we have to increase temperature. But when delta H is negative, delta S, if you are confused at this point, both online and non-online, if you are confused at this point, just close your mind. Just come to this level and leave it here. But I'm only talking about this because of those that can think about it. Most likely, if you see question here too, it happens, but it's in your past question. You will see. You will see when we start solving questions. Questions make it more clearer. So now, if delta H is negative and delta S is positive, you already know the condition. It will always be what? Spontaneous. Abi? Because this makes it spontaneous, Abi. This also what makes it spontaneous. So this will always, so you don't need to change anything. You don't need to increase or decrease temperature. It will always be spontaneous. But now, if delta H is negative and delta S is negative, will this be spontaneous? You will say it depends. Delta H be negative, if it's spontaneous. Yes. Delta S be negative, if it's spontaneous. No. But what will make it spontaneous? Since this one is negative, then you have to decrease the temperature. For this one to go from liquid to ice, what will you do? Decrease the temperature. Abi, if you increase temperature, mama melts lots in it. Are you getting my point? So yeah, that means that for this one to be, you have to what? For this one to be favored, when this one happens, you have to increase temperature. Then for this, you have to decrease temperature. Just focus on the delta H part. That's all you need. If delta H is positive, you know it's most likely not going to happen. And it is endothermic, so you need to supply more heat. Then you have to increase temperature. When it is negative, then most likely going to happen. But if you check delta S and it's not favoring it, then you have to take away heat because it is exothermic. Those are the three conditions: condition 1, condition 2, condition 3. So you can now go and think about that more after this. But if you know your brain, you don't like stressing your brain, and you want to study medicine, and you don't like stressing your brain, I love you. I love you so much. If you want to study medicine and the lights, competitive courses, you will have to stress your brain. You will have to let your brain work. So don't say, but for jam, some people might not know this and enter school and enter medicine. Yes, there are some things people don't know and they will still make their desired course. So the ones you know, just know it well. It's not everything you have to know at once. So quickly, laws of thermodynamics. The first law states that law of conservation of energy. So first law of thermodynamics, that's the next thing. The first law states that energy can neither be created nor destroyed, but can be transformed into it can be transformed from one form to another. That is first law. Energy can neither be created nor destroyed, but can be transferred from one form to another. So this is called the total energy or internal energy from the first law. There are a lot of stories to say here, so I've said it when we're treating the mock. This one is your enthalpy, and this one is the work done. So work done cannot be work done on the system or work done by the system. Just know that they can just give you the formula and ask you one or two things. They might not really say you should solve questions here, because there are some things you need to understand to solve questions, and we don't have that time now. Then second law just means that the universe is always accompanied. Universe is always accompanied by an increase in entropy. Universe is always accompanied by an increase in entropy. Disorder is always the state of the day. That's what that means. Disorder is normal in life, but order is not normal. Yes, disorder is the state of life. What happened here? Going from ice to liquid, can it happen on its own? Yes. So things going from order to disorder is natural. But things going from disorder to order, you will have to work. That's why if you see people misbehaving anyhow, sometimes it's just natural. It will take the ones that already have the brain and the spirit and mind of God to do things in order. Everybody is terrible. Everybody. So that's why I should not judge anybody. The things I want to do are not the things I do. But the things I don't want to do are the things I actually do. Disorder is normal. So you just have to take conscious efforts to put things in order. How many of you cleaned your room before you left this morning? Do you even have a room? Now, this is it. If you clean your room now and you go out, when you come back in the night, some part of your room would have been dirty. But let's say you leave your room dirty before you left. When you come back, will your room have been arranged? So that's the only condition. Richard, happy birthday in arrears. God bless you. I've been expecting cake since yesterday. We have not seen. So, order, disorder. Disorder is the normal thing. So, it's not normal for things to just go into order. That's why you have to put work. You see why you are not knowing chemistry is because you are not ready to put the work. It's easy for you to actually say that, I want to play game. But that moment you carry book, you start sleeping. Throughout yesterday now, when I was doing some other work, but bí mo ṣe gbé biochemistry like kò tí to 30 minutes. So that is the thing. For you to go to school, it takes conscious effort. For you to know book, it takes conscious effort. But to go to TikTok and spend 24 hours, you just keep scrolling. So that is the thing. And for you to have money in life, it takes what? Conscious effort. So to become someone important in life, it takes effort. But to become rada is very easy. Just enter market. Oh yeah. Your teeth will get dirty naturally, but your teeth will never get neat naturally. All those are the things. But in terms of chemistry now, disorder is the order of the day. Delta S is equal to delta H over T. I've given you that formula before. So that's all about its energy. So for 10 minutes, let's quickly look at questions. Oh yeah, your past questions, quickly. So today I have introduced you to thermochemistry, a quick summary. And I told you that it is the study of heat changes accompanying chemical reactions. Abi? Then I also said that please let there be order. I also said that hello, let's keep quiet, please. This is the first topic. We still have a lot of topics. Don't let's waste energy. Just bring out your past question. That should not bring noise. And open is less than bond forming energy. That is what? Exothermic. When the lattice energy is less than the bond hydration energy, that is also what? Exothermic. Opposite of everything is endothermic. When delta H is negative, it is what? Exothermic. Is that taken? Then I said, how do you measure this heat that is given or heat that is taken? We call it N as the amount of heat evolved or absorbed by a system into the surrounding. Then I said we have what we call standard enthalpy of formation when 1 mole of a substance is formed. Standard enthalpy of combustion when 1 mole of a substance is completely burnt in oxygen. Standard enthalpy of neutralization when 1 mole of hydrogen ion reacts with 1 mole of hydroxyl ion to give 1 mole of water. Neutralization. Standard enthalpy of reaction when reactants come together to give products. Then I now said for combustion and neutralization, it is always exothermic. Then for reaction, it can either be exothermic or. Then when you solve questions on combustion or neutralization, your answer must always be negative. Even if your final answer is positive, you must pick a negative answer. Then from there, we did some bit of calculation, and I said for Hess law says that the sum of the heat energy is always the same. Either the reaction takes a single step or several steps. That without external assistance. That's what that word means. Spontaneous. It will happen on its own without you supporting it. But when it so let's do number 6. We are doing number 6 because we didn't solve it. I gave you a formula that delta Hc is equal to Q over N. Abi? So let me read the question. 0.16 gram of methane when burnt raises the temperature of 100 gram of water by 40 degrees C. What is the heat of combustion of methane if the heat capacity of water is 4.2 joule per gram per degree Celsius? So now let's look at it. Anytime they ask you a question on heat of combustion, I gave you a formula. What's the formula I gave you? The heat of combustion is given as Q over N. And I told you that Q is equal to MC change in temperature. Abi? But note something. you carry out this reaction in a calorimeter. This is a calorimeter, which is an isolated system. You are going to have what we call a stirrer in that place. You are going to have a thermometer. So this thermometer reads the temperature. Now, this is the stirrer. So if I want to measure it on combustion, I will now put the flask, whatever flask it is, or a closed flask. What am I measuring the heat of combustion now? Methane, Abi. Please listen, I'm explaining this so that when you see questions, you know how to approach them. You put methane here plus oxygen. Methane plus oxygen will give you CO2 plus water, Abi. Now, from what we have here, I think that equation is not okay. That's okay now. So now, when you burn 1 mole, so this is what you need to focus on. They now said you should calculate the standard enthalpy of combustion of methane. Is that taken? That's the question. This reaction, will it be exothermic or endothermic? We already said combustion is always what? Exothermic. We are applying what we have learned now. So they now say calculate the standard enthalpy of combustion of methane. So this is what they do. They will put the flask inside this place, and there's water. We did the experiments in UI 200 level. So you put the flask inside this place. The water, you will measure the temperature, the initial temperature. Let's say it's at 1. Thermometer will tell you. Then when you now put the flask inside, this reaction will start taking place. Then from the boundary of the flask, heat will be given to the water. So the heat evolved is inside water now. The temperature of the water will start changing. Then at the end of the day, when the reaction has taken place, you can measure the new temperature. That will be the final temperature. Abi, the water inside this place, you would have weighed the mass. So you will know the mass of the water. Is that taken? So there's already a change in temperature, Abi, and there's mass. Then this water, you will be given the specific heat capacity of that water. So now, to calculate the enthalpy of combustion, amount of heat given by this reaction, I need to know the mass of the water, which is what this part represents. Mass of the water, the specific heat capacity of the water, and the temperature change in the flask. Do you get that? Over, what does this N now represent? The amount of this guy that is burning. So that will be number of mole of methane. And number of mole of methane can be mass of methane over molar mass of methane, depending on the question. So now, let's solve this question now. So from what we have, please, that's number. You are given the mass of methane, Abi. So that means we can determine number of mole. So number of mole of methane is going to be mass of methane over molar mass of methane. Mass of methane is 0.16 gram over molar mass of methane, 16, Abi. That's 12 plus 4. That's 12 plus 4. That's 16. So divided by 16, and that should be what? So the number of mole of methane is 0.01. So let's calculate the quantity of heat that is given out now. And that is equal to mc theta. So now what would that be? Mass of water given is what? Be careful now. All of them are in gram. C is in gram. Check the units. Your specific heat capacity is in gram, Abi. Mass of water is in gram. Mass of methane is in gram. So everything is okay. So I can say 100 times, what's my C now? Times, what's the change in temperature? Now, don't forget, they said that it raised the temperature by 40 degrees. That means that is the change in temperature. Maybe it was 60 before. If the initial was 60, then the new one will be 100. Share. So it raised it. And whenever you are doing change in temperature, you don't need to convert. Is that taking? You don't need to go and change it to Kelvin again. Change in temperature. So, and you can see the unit of C is already in degree Celsius. So multiply it by 40. What would that give us altogether? 16,800. So for Q is energy. Is this going to be in joule or kilojoule? That is joule. Look at the C you are given. What's the unit of C you are given? Joule per gram per degree Celsius. Abi, that means your final heat is the amount of heat. She gets. So the unit is joule, is work done. You did it in physics now. So now, from what we have here now, I already have my Q. So I can calculate delta 8C now. So delta 8C is going to be Q over N. And that's going to be 16,800 all over 0.01. That means you have to divide it by what? 1,000 to convert it to kilojoule per mole. But you see my final answer now is positive, Abi. What will I pick in the option? A negative answer. If you pick the positive answer, you will be wrong. Is that speaker plugged? Is it plugged? Normally, is it charged? They didn't show you the sign. But it should be there. It should be there. So please, let's not forget that. Is that taken? So please don't forget that. Oh, everybody. Number 7. Do we understand this now? Please, now I need you to respond. Do you understand this? We have explained it. So number 7. In the reactions, the thing is that you can learn a topic over and over and not still understand. But when you learn a topic and you solve questions, and you're able to solve several questions, that is when you know it. So that's why I will still take my time to solve questions. I won't just stop on and just teaching you, because those questions are more important than the stories I've been saying since morning. So I don't know why this guy is cracking. So number 7, in the reactions, have you seen the reaction? What is the delta H for the first one? Minus 286. What's the delta H for the second one? Now, the minus sign is just an indication of something. And what does that indicate? It's loss, Abi. So it's just an indication. It has nothing to do. So let me ask you the first question. In the reaction 2 and reaction 1, where do you think it is lost the most? Reaction 2. You know, it is normal to say that minus 100 is greater than minus 200. I don't know if you understand what I'm trying to point out. But that negative is just telling you that it was given. But what amount of it was given? 400 and something. So there is more heat in 2 than in 1. Show you? Yeah. So let's look at these equations imply that A, I think we have answered that. A, more heat is absorbed. Heat is evolved. Oh yeah, yeah. 2, more heat is absorbed in 2. C, less heat is evolved in 1. Yes. Reaction 2 proceeds faster. That does not mean now. So more heat is evolved in 2, less heat is evolved in 1. Are we cleared now? Yeah. So our best answer is what? Option C. Shotiye? I know why I'm saying it over and over, because people used to get confused here. When they see minus 2 something and minus 4, they feel minus 2 is higher than minus 4, which is true. But the minus there, first remove the 2. Between 4 something and 2, which one is more? 4. The minus is only telling you that it is given. Show you all these are simple things that people get confused about. I've been there, so I know what I'm saying. That's why I'm hammering it and hammering it without hammer. Number 8. Look at this question. I think we have answered that before. Number 9. Can we move on? Number 9. The diagram above shows the energy profile for the reaction form. It is clear that the reaction is what? Exothermic. What is the value of delta H in that reaction? Everybody look at it. We are all in this class together. Nobody is brilliant now. Nobody is brilliant. All of us are now the same. And everybody, after this class, there are some parts of chemistry that should be meaningful to you. So it is just for you to now go and practice till the day of your exam. Don't sleep on it. So number 9 now is what? Minus 20, Abby. And the reaction is what? Exothermic. Because the reactant is higher than the product. Are we clear?
Yes.
Number what now? Number 10. In dilute solutes, the heat of the reaction is what? Look at it, oh. I think it was like what I even explained the other time. In the dilute solute of the reaction, that is minus 57.3 kilojoule. Then, what will now be for the second one? Do you all understand that?
Yes.
You know the first one is just 1 mole.
Yes.
And the second is how many moles? 2 moles. So if the first one that is 1 mole is 57, then 2 mole will be 57 times 2. Show ye?
Yes.
Number what now?
Yes.
Number 11. The energy change for the reaction is this. So what are they asking you to do here? Calculate delta H of reaction. And what is delta H of reaction? Delta H of product minus delta H of reactant. And they gave you something here. HCO is what? Delta H of formation of CO. Are you there? All these things means that you have sense. When you are speaking, when you are teaching chemistry, many of you want to become teachers in the future. So when all the teachers in this class, praise the Lord. Yes, teaching is an amazing profession, especially all you female. Instead of all of you to go and become teachers and impact the generations coming, let men be doing like that. You will have time to enjoy your life as a female. You will have time for your family. You will have time to enjoy your children company. You will have time to enjoy your life. You will have time to go on vacation. You might not just have much money, but just pray that your husband have money too. Okay, the support is okay. You shall enjoy yourself. That's what female are for. You have to enjoy life. So let's move on. So teaching is a good profession. All of you, it's because of Nigeria. You need to know how much teachers are getting abroad. You better study education and move to US. Can you solve that question? We should solve it together. Number 11, quickly. We'll move on to the next topic soon. So when you get home, I will solve maybe up to 20. Then you can go home and practice the rest. Then anyone you cannot solve, you can message me. I'll just solve it on YouTube on a paper and I'll post it for everybody to go and watch it. So number 11, they said we should calculate the. Are you sure that speaker is still on? Is that speaker on? And it's blinking. Is it blinking? Is it charging? I'm not sure that it's charging because it's not even picking anything. So can you hear me? There's no need for mic. Yaruka, have your seat. Thank you. There's no need for mic for now. I'm using mic for the online, so you here should listen. And please listen to me. So let me write out the reaction first. CO gas plus half O2 gas to give CO2 gas. So now they said I should calculate the standard enthalpy of this reaction. Please don't stress my brain when you talk too much. You are given the standard enthalpy of formation of CO. You are going to be making me to overshout if you are talking. and we have a lot to do today. So one of the things you have to enjoy now, please. I'm not using mic and I might have to be over shouting if you are talking. And I still have a very long way to go. I still have a lot of children to give birth to. So please, from what we have here, delta H not CO2. Why is it that we are not given that of O2? Because the delta H of formation of an element is 0. So now, to calculate the heat of this reaction under standard condition, we are going to have sum of the number of moles of heat of products minus sum of the number of moles of heat of reactants. So now, what's my product? CO2, and it is just 1 mole. So I need to know that of CO2 minus that of CO. Is that taken? I'm not involving O2 because it is what? An element. Oh yeah, let's put the values. You know why all these brackets are important? So that you don't misplace values. So now, delta HR is now going to be products CO2. That's minus 393 minus 1104, right? 0.4 minus times minus 393 plus 110.4. That gives you what? 2. What's the unit? Kilojoule per mole. Is that okay? So don't let us misplace it. Let's solve number 12. Now, 20. Have you all understood this now? Yeah. That's how you solve it for reaction. Number 12. 20 cm cube of 0.1 molar ammonium hydroxide solution, when neutralized with HCl, liberated 102 joules of heat. Calculate the heat of neutralization of ammonium hydroxide. It's liberated 102 joules of heat. So now, let's balance the equation. Normally, if you have practiced very well, although there's no negative here, when you release 1 mole of water, usually it is always around 57 point something. So this question might not have typed it well. Sure you get. But if you calculate, you can get 1. But if you have practiced very well, you already know neutralization should be negative. And the only negative answer is option A. You just pick it and you move on. But you make sure you note it so that when you still have time, you now come back and do proper calculations. So, do you understand what I just said? So, can I rub this part? Oh yeah, let's do it. Ladies and gentlemen. Let's balance the equation. Ammonium hydroxide plus HCl to give ammonium chloride plus water. Abi, 1 mole of water will be given. So now, if you have 1 mole of water, they said that joules of it, that's QO, Abi. That means you have 102 joules of heat. That's what was released. They now said that calculate the heat of neutralization of ammonium hydroxide. But note something, you are given 20 cm cube of 0.1 molar ammonium hydroxide and 20.05 cm cube of 0.18 HCl. Can we do something? Calculate the number of mole of ammonium hydroxide. That will be volume times concentration over, and that will be concentration in 0.1 times 20 over, what would that give us? 2 times 10 raised to power minus 3 mole. Are you following? We want to compare their mole ratio so that we know what to do. Actually, we have been given the mole. So the number of mole of HCl is equal to concentration times volume over 1000. And that is what? What would this give you? Times 10 raised to minus 3 mole. So now that we have the mole compared, their ratio is 1 to 1. Abi, I want to see the one that will be in excess. Which one is in excess? That should be HCl, Abi. So that means this is like 0.002, Abi, and this is 0.0025. Is that correct? That should be 205, Abi. This one is in excess, and we are calculating for this. So that means that if I use 0.02 of this, I will also use 0.02 of this, Abi. What will be left for this? Abi, in excess. So this is number of mole that I have. So if 1 mole gives this joule of energy, then how much will this give? So I can say my delta H of neutralization can be Q over N. And I think that should give me 102 divided by 2 times 10 raised to power minus 3. That would give me what? Joule or kilojoule? Per mole. Abi? Then I can divide by 1000. That will give me what? 51 kilojoule per mole. Will it be positive or negative? So my answer will be 8. Now let me go back to what I did here, because some of you know the formula. Q over N, Abi. I gave you this formula when I was teaching you that to calculate the standard heat of neutralization or combustion, you can use this formula. Q represents the heat, the work done, Abi, and you are given that. N represents what? Number of mole. Then the question says that calculate the heat of neutralization of this guy. You know why I had to do this first? In case that this